Very good evening to one and all, and welcome to this special public webinar, which we are organizing as a part of the School Outreach Program, jointly organized by the National Academy of Sciences, India Delhi chapter, and the Deen Dayal Upadhyay College, University of Delhi, under the aegis of the DBT, that is Department of Biotechnology's Star College Program. Today, we have with us in this evening webinar, Dr. N. Lakshminarasimhan, who is from the Electro-Organic and Materials Electrochemistry Division of CSIR Central Electrochemical Research Institute, Karaikudi, Tamil Nadu. And currently, he is a Fulbright Scholar at Professor Mas Subramanian's Research Group Department of Chemistry, Oregon State University, US. So he'll be talking to us on a very interesting topic, inspiring science for aspiring minds. So before inviting Dr. Lakshminarasimhan for delivering his talk, I would like to introduce him to all the attendees. So it's my pleasure to introduce Dr. N. Lakshminarasimhan, the principal scientist from CSIR Central Electrochemical Research Institute, Karaikudi, and associate professor at Academy of Scientific and Innovative Research, Ghaziabad. His broad research area is solid-state chemistry and material science, and his work focuses on functional materials for energy and environmental applications. He's actively involved in understanding structure, morphology, property relationships in photofunctional materials, including phosphors, photocatalysts, and dye-sensitized solar cells, electroceramics, and energy materials. He studied at Muthurangam Govt Arts College, Vellore, and obtained his undergraduate and postgraduate degrees in chemistry from University of Madras. He obtained his PhD from IIT Madras, Chennai. Further, he carried out his postdoctoral research work at Pohang University of Science and Technology, South Korea, before joining CSIR-CECRI. He has 49 publications in international peer-reviewed journal, and his H index is 22. He is the recipient of CSIR Young Scientist Award in Chemical Sciences for the year 2012, which is first of its kind in the history of CSIR-CECRI. Currently, he is a Fulbright Scholar at Oregon State University, USA. With these words, I now invite Dr. Lakshminarasimhan to kindly share his screen and then we'll stop.
So good evening, everyone, and thank you, Professor Saxena, for organizing this wonderful event to motivate our school children through this 2 months long program by having several eminent experts in different fields to connect all branches of science and technology. And also, I thank all the students and for your kind active participation in this event, which is useful for you, and also for adjusting my time. So because even though it's a Saturday evening, 7 o'clock, so still people are ready to listen. And thank you, Prof. Saxena, for this opportunity. I thank all the organizers of this event for this wonderful program by NASI and Deen Dayal Upadhyay College. Okay, so my topic I'm going to talk about, I'm not going to talk too technical anything, just to say inspiring science for aspiring minds. That is, the science inspires the aspiring minds. How the science is very important, or how it motivates us. So most of them are from the nature or from whatever is in the surrounding. So that's how people have discovered several things. So that's what I'm going to give with a few examples. So I hope it will be useful for you to just get motivated. So before moving, let me thank all my teachers, professors, and mentors. So far, I'm here at this stage because of the knowledge that they imparted in me. And also, I'm thankful for the project staff and students who worked with me, and the director, CSIR-CECRI, Karaikudi, for all the support and the continued support and motivation for us to do such wonderful programs. So Our institute, CSIR Central Electrochemical Research Institute, is one of the 38 labs of Council of Scientific and Industrial Research. So ours is in the state of Tamil Nadu at the southern corner here. And this institute was founded in 1948 by the great visionary Dr. R.M. Arappa Chettiar. So it was having an area of 350 acres or 1.5 square kilometers. So it was founded in the year 1948 and started functioning from 1953. Currently, we are about 110 scientists and 100 scholars and some project staff who are actively involved in various aspects of electrochemical research, because all the CSIR labs have been started with some focus. Some labs focus on the chemicals, some labs focus on the physical properties, physics-based material and bio. And this institute, so just in the year 1948, someone comes up with the idea to initiate an institute for electrochemistry. So because it's the energy. So whatever we are using now, the batteries, all applications based on the electrochemical aspects. So we have a nice campus, so you can find a lot of peacocks walking around and dancing in the campus. So if you have any chance in the future, you can visit our campus. So it's a nice campus. Okay. So in this institute, so what I have been working on the functional materials for energy and environmental applications. So I've been trained in my PhD in the branch of solid state chemistry and material science. So I use the knowledge gained in the area of solid state chemistry to design and synthesize materials and to understand the structure property relations, mostly in the photofunctional materials. That means the materials exhibit their properties or the functionalities and only under when you shine light on them. So for example, photocatalysts or the phosphors which we use in the light emitting diodes. So I will talk about this, and transparent conductor, etc. Or also since I am in the Electrochemical Energy Institute, so I also work in collaboration on energy materials like batteries or supercapacitors and magnetic and dielectric material. In all these aspects, my focus is to tune the properties of the functional materials by using either crystal structure or the surface structure and the composition of materials and the morphology, the size and shape of the material that controls the properties. So this is just to show you what I've been doing at CSIR-CECRI. So now let us go to today's topic. First of all, I just want to define what is science. So if you look at the Oxford English Dictionary, so we all study science. So why do we study science and what is science? So according to Oxford English Dictionary, so science is defined as the intellectual and practical activity encompassing the systematic study of the structure and behavior of physical and natural world through observation and experiment. So we are going to study the physical or natural world around us. If, for example, if we see the plants, the leaves are green and the plants are green and they do the photosynthesis. So then we start to understand, we try to understand what makes this, how it converts the carbon dioxide into carbohydrates. So glucose, fructose are the carbohydrates, and that we consume as food. So this process led to the discovery, or it went to understanding of the photosynthesis, photo processes taking place, or that now we are using it to convert the CO2 to other useful products. So by means of the photochemical or photoelectrochemical methods. So that's how our understanding goes from the natural world to the laboratory. Or we can also say science is a systematically organized body of knowledge on any subject. It may be chemistry, it may be physics or biology or any subject. So it's a systematically organized body of knowledge, what we have now. So that's what we study in our schools or colleges. What's the science, what is the different subjects. So according to Albert Einstein, whom you know, you're studying in your higher secondary, maybe in the class 12, that is a photoelectric effect. So according to Albert Einstein, the whole of science is nothing more than refinement of our everyday thinking. So today we may find some answer for some of the natural phenomena, but then we'll refine our mind. We keep on thinking whether it's right or what is the experimental proof we have it to prove this. So that's why it is a refinement of everyday thinking. So Albert Einstein name, as I mentioned, you come up with photoelectric effect. That means when light meets matter. So what happens when light meets matter? So it's before that, I just give one more example here. So it was Michael Faraday, so whom again is considered as a father of electrochemistry. And not only that, in the magnetism, he has given several laws and he has made the first electromagnet. So this was shown here in the photograph is the colloidal ruby gold. It was prepared by Michael Faraday in the year 1857. So you may wonder why he is interested in preparing a gold solution, because his interest was to find out the experimental relations of gold and other metals to light. We normally know that glass is transparent to light, but the light, if you shine on a metal, it's going to get scattered or reflected. So how these metals behave. So for which he has taken a gold chloride and he used a phosphorus as a reducing agent in carbon disulfide. So then the gold 3 plus gets reduced to metallic gold, AU0. So because of the reducing agent here, and since you have the sulfur-based solvent, normally the gold has strong affinity towards sulfur. So this settles and it caps here. So you don't see any of the particles here. So that's why in his paper, which was published in the year 1857, he called this as a very minute in their dimension. So you cannot see the gold particle. They may be very small. Now we can imagine nowadays we call them as the nanoparticles or nanoclusters. So at the year of 1857, the word nano was not known at the time, and there was no experimental tool to view the objects of the dimension in the nanometer scale. So this same chemistry is used nowadays. So we use, instead of simple carbon disulfide, you can replace this with a long alkyl chain sulfide or thiol group, that is such containing long alkyl chain groups. So that can anchor this gold and stabilize a very small clusters of gold, few atom clusters of gold. The same chemistry which has been extended. Okay, now after this, so there is a photoelectric effect, so which was carried out first observed by Heinrich Hertz and Philippe Lenard in the year 1887. So what they have done is they've taken metal and they shine light on a metal. They found the electrons are ejected from the metal. So this is the experimental setup. Of course, I have taken from the class 12 physics textbook. So you take an evacuated glass tube. So you have this photosensitive plate, it's a metal. So when you shine light on them, so what happens is the electrons are ejected, so which you can measure here. So then there was a problem. So we know that the light is of having a wave nature, but then once you have the wave, then you should also get back the waves, okay? But it's contradictory to the wave nature of light. How you get an electron, which is a particle. So it was Albert Einstein. So in the year 1905, he proposed that the light can be considered as a particles. So it has particles with the energy of h nu. So we call them as photons. So when you have some of the wavelengths, not all the wavelengths, some of the wavelengths, when it falls, it depends on the energy. So then you see the electrons are ejected. So he has found out there is measured the kinetic energy of this electron, and the amount of electron ejected depends on the energy of the light and the work function of the metal. So how easy it is to remove the electron from this metal, that's called your work function. So he explained this photoelectric effect, and in 1905 he published 3 important papers. So it's called the year of miracle, that's Annus Mirabilis. So, and in the year 1921, he was awarded the Nobel Prize in Physics for his contributions to theoretical physics, and mainly for this photoelectric effect, explaining the photoelectric effect. So coming again to the light, so we have another name, Sir Chandrasekhara Venkat Raman, so Sir C.V. Raman. So we know very much about him, and he was born in the year 1888. So his research interests because of his research interest, even though he was working in accounts office, so he used to have a small lab. So he in Kolkata, so he used to work from morning 5:30 to 9:30 in the lab, again from 9:30 to evening 5 in the office, then again 5:30 to 9:30. So that's how he worked 16 hours a day. So because of his interest, so he was appointed as a research professor at the age of 28 at Calcutta University in 1917. But in 1921, he was traveling to the Oxford University to attend a University Congress of University, the meeting organized by the ministry. So he was traveling in the Mediterranean Sea in a ship. So then he saw why this beautiful sea, then what gives the color, the beautiful color. So that was a question he found out. Why does sea look blue? Though it was explained earlier that the blue color of the seawater is just a reflection of the color from the sky, which looks blue. But then he had a doubt, is this right answer for this? And that's the way what I define here as a scientific look or scientific way of thinking. So whatever we see in our surrounding, you should think in a scientific manner. So there are reasons for everything. If you understand the scientific reason, so you can explain anything. So there's nothing which works without science. So there will be scientific reason. So that's how he looked at this color of sea, why it looks blue. So that question made him to think. So what was explained before by Lord Rayleigh is that, so the sunlight, we know it gets scattered by gases in the atmosphere, and the blue light is this one which is scattered most, and so we see the sky as blue in color. So, but this Rayleigh scattering is elastic. That is, whatever energy you give, you get back. So throwing a ball on the wall and the ball comes back. So he said it is elastic. But later it was Arthur Compton who said it's not elastic, there is an inelastic scattering. So both of them received Nobel Prize in physics at different years. But Raman then, because of his question in his mind, he came back and started some of the experiments. So in the year 1921, but they found a strong color change when the light is scattered by glycerol. See, they send a blue light through the glycerol solution, but the light that is coming out is a green light. So what is happening then? Why there is a change in the energy? So if you take any molecule, so you can see here, they will be always vibrating, okay? Because we have some thermal energy that's enough for the molecules to vibrate. The bonds will be stretching or bending or vibrating. So when you take such any solution, so you shine a light, for example, okay, so here you shine a light, then what you get out of that is, if you shine a blue light, because of the vibrations, so some of the energy is absorbed and you get back the green light. So that is what he observed in the glycerol. So they explained. So if you look at here, you know that, so it was the Rayleigh scattering, whatever energy you are giving, you are getting back the same energy. But then it is not possible. So some of the energy is lost. So because this has a different energy, the blue light compared to the green one. So blue has higher energy, whereas green has a lower energy. So that energy is taken by the vibration of the molecule. So if that is the case, then you call this Stokes. So if it is opposite, sometime it may be reversed. The energy may be given from the molecule. So then it is called anti-Stokes. So this is the basic principle of the Raman effect. So how the color changes of the light. So that's how now he could explain why the seawater is blue in color. And this is the spectrometer he built on his own. So Raman, this original spectrometer, and it's here he was explaining to many of the foreign scientists who visited him at Bangalore. And yes, so this is just to show his classroom and his visit to the school to motivate the children, like what we are doing today. So he was a much celebrated scientist because he was the one and only scientist who got a Nobel Prize in physics by carrying out all his work in India. Okay, so he never worked abroad, so he worked in India. So if you look at Raman's statement that the real growth of a country was in heart, mind, bodies, and soul of young men and women of the country. So in his Nobel lecture, he mentioned that in the history of science, we often find that the study of some natural phenomenon. So for example, he was thinking why the seawater is blue, it's natural. So he tried to understand. So studying some of these natural phenomenon has been the starting point in the development of a new branch of knowledge. So that's why I call here science is inspiring while studying nature. So that's what we all do it. Why it is nature, how we mimic the natural process in useful in our day-to-day life by making them in a form of device or in different forms. So here it's a Raman spectroscopy which has been developed later. So we can see it is useful now to differentiate whether you have a nanocrystalline of the carbon, one of the form is diamond, or you have a crystalline form of the diamond. So you can distinguish the crystallinity or the amorphous or nanocrystalline materials from the Raman spectrum. Of course, it was for some time, it was not used much, but once the laser was discovered, now the application of Raman spectroscopy has been several fold. So that's a laser is now used as a light source now. So we call laser Raman spectroscopy. So we can find its applications. Like for example, this is a simple Raman spectrum of any molecule. And you can also use this to image the molecules on the surface of any metals. Like for example, if you take a gold or silver substrate surface, then you can add some of the molecules. So initially the molecule, if you take separately, the signal will be very poor, but once you have it on the metal, so then the signals will have a higher intensity. That's called surface enhanced Raman spectroscopy. Also, we can use this Raman spectroscopy to study the human tissues. So how you can find out what are the different constituents of the human tissue. So these are the several applications which has become as a part of the discovery of Raman effect and the Raman spectroscopy with the use of lasers. So that has revolutionized further. Okay, coming to this. So we have another name, Sir Acharya Sir Prafulla Chandra Ray, who is considered as the father of chemical sciences in India. So he was the founder of Bengal Chemicals and Pharmaceuticals. So this is the first pharma company of India. So he obtained his Doctor of Science at the University of Edinburgh. So his thesis was on conjugated sulfates of the copper magnesium group. So we call double salts. So he a study of isomorphous mixes and molecular combinations. So not only that, he's famous. He has come back. He started his career as an academician. So he first discovered the mercurous nitrate in the year 1896 by dissolving mercury in nitric acid. So you could get the mercurous nitrate, which has received a wide attention from the world. So later he started his own companies for then pharmaceuticals. So he is considered as the father of chemical sciences in India. So you should remember this name as well. Okay, so this week, as we have seen from the 4th of October and even coming Monday, so we have the Nobel week. That means the Nobel Prizes are announced in the first week of October of every year. So this year for the physics, so it was awarded to Shiguro Manabe, Klaus Hasselmann, and Giorgio Parisi for the discovery of interplay of disorder and fluctuations in physical systems from atomic to planetary scale. So these two have made some of the mathematical calculations to predict the global warming as well as the conditions of the environment. So that is how it was useful for several years. So to find out the global warming, etc. So that is how they got this Nobel Prize. And in the chemistry, it was Benjamin List and David Macmillan. So for their development of asymmetric organo catalysis, so which we'll see in a little later. And for medicine or physiology, it was David Julius and Adam Patapushian. So for their discoveries of receptors for temperature and touch. So whenever our body reacts, the temperature rises. So what is the sensor that's how that is happening in our body, as well as if you have somebody touches, okay, how do we feel? How we sense this? So there is a change in the like a piezo. There is a mechanical change that allows some of the signals go into our brain. So this is a contribution made by them for the medicine or physiology. So it was why this Nobel Prize, if you look at Alfred Bernard Nobel, so he is the inventor of dynamite, but he was making this for making blasting rocks or drilling tunnels. But he had his factories at 90 different places in more than 20 countries, and he has 355 patents. But at the later stage, he realized that sometimes it is also used for destructive purpose. Then he wanted to make sure, so he has written a will that his properties from the interest, so whatever come, so shall have conferred the greatest benefit on mankind. So he made this will that this money can be given us in the form of award for those who have made some of the contributions that shall have conferred greatest benefit on mankind. So that should be useful for the mankind. So that's how the Nobel Prizes are awarded every year. So this year, in chemistry, it is for the Benjamin List and Macmillan. So asymmetric organo catalysis. So they first published papers in the 2000 year, in the year 2000. But then there was called the year after that, it's organo catalysis gold rush. So that's simply like if you want to make a table and chair. So normally you take a wood and then you sculpt that and take these pieces. But there is another way, adding them smaller and smaller and fixing them. Now you may also see how they easily make these things. So not by taking a bigger wood. Now you can make small pieces, you can make separately the legs, then you can attach. So that's how they use. Normally in any of the catalysts, so enzyme catalysts, enzymes can be used or metal catalysts are used. But what Macmillan and Ben List made is the organo catalysis. So they call it only organic molecules, simple molecules with having a nitrogen atom, so that can form an iminium ion, which can attract electron and release. So this kind of molecule without any metal, so this can be useful to construct large organic molecules. So that's why it was very important. So usually they call the chiral molecule. We know chiral is that one which has a non-superimposable mirror image. If you take it to your hand and a mirror, it won't superimpose. Okay, so mirror image, so handedness. So for example, here it is a limonene molecule which has two different forms. So one is like this, it is in the lemon, whereas the other form, for example, these molecules are here. So it's a mirror image that is giving the flavor in the orange. So same molecule, but different form. They have non-superimposable images. So that's how they use this chemistry. So you can find more information at the nobelprize.org on this type of discovery, how they made it. Okay, when we talk about the carbon, again, we have different forms of carbon as you have studied the allotropes, like diamond and graphite are the allotropes of carbon, but we have other forms as well. So diamond, we know the carbon has a sp3 hybridization and each carbon is connected to other 4 carbons. So that's the beauty of the carbon, the property called catenation. So it can form the bond with all its 4 valence electrons and continue. So whereas in the case of graphite, it has each carbon is surrounded by 3 other carbon. So you have 1 electron free, so that forms a pi bond. So electron can delocalize in these layers. But it is a layer structure. The layers are held by van der Waals force. But you can also separate them. They form a graphene, or it can also be rolled into carbon nanotubes, or also as a fullerene C60 molecule. So if you look at the discoveries of various carbon, it was in the years 1970s, where Harry Kroto and Dave Walton, they were involved in the synthesis of long carbon chains, only carbon molecules, okay, I mean carbon atoms. But later they found that they discovered the buckyball, which has 60 carbon atoms. And similarly, in the 90s, the Japanese scientist Ijima, who observed a multi-wall carbon nanotube when he was analyzing some of the carbon samples. And in 1996, the Nobel Prize in Chemistry was awarded to Harry Kroto and Robert Curl and Smalley for the discovery of the C60, the buckyball. And similarly, the carbon nanotubes also started finding application in by Samsung used in flat panel display, or the IBM is making the single carbon nanotube for the transistors. And it was in 2010, Andrew Geim and Konstantin Novoslev, so they were awarded the Nobel Prize for in physics for their way of separating the graphene from the graphite, so which has changed a lot more applications. So it is a two-dimensional sheet, and it has a very good conductivity and other properties. So that's why it has become a Nobel Prize winning work. So if you again look carbon C60, so there are 60 carbon atoms arranged in the form of a buckyball. So they could find out from the mass spectrum only the molecules with 60 carbon and 70 carbon. So they are all stable. So that's how they discovered this. So 60 is more prominent compared to the C70. So how these are arranged is, see, if you have it has a 20 hexagons and 12 pentagons. The pentagonal surface is required to wherever you want to bend it, so that you get. So it was the architect Buckminster who made this kind of structures. So they just named this also as a Buckminster Fullerene. So again, you can look at the symmetry. So whether you have a 5-fold symmetry or a 6-fold symmetry. So that is also another important concept in the science of symmetry. So if you take a snowflake, you can have a 6-fold symmetry, you have a hexagonal kind of thing. If you rotate by 60 degrees, you get the same structure. So you rotate from along the axis, so you can rotate by 60 degrees, you get the same. Another 60, you get the same. So it is a hexagonal symmetry. But the 5-fold symmetry, which exists in the nature, you can see here there are 5. So if you rotate by 72 degrees, so you get here and then you get here. So of course, if you have the leaves are same size and the same dimension, then you can call 5-fold symmetry. So again, it was also discovered by another scientist, and Daniel Sheschman, so which was awarded the Nobel Prize in Chemistry in 2011 for called quasi-crystals. So initially it was thought 5-fold symmetry is not possible, but later he showed that it is possible with certain elements which forms the 5-fold symmetry. So that's nature also has such a symmetry possible. So we call here, like we take Taj Mahal. So we say it's a beautiful because it's symmetry. See, for example, if you take from the middle, so you go whether on the right or on the left, so you have the similar structure. So you have 2 pillars here. If you remove one, it won't look beautiful. So symmetry adds beauty to objects. Symmetry is nothing but an abstract concept associated with harmony. So when you go from this side or this side, you have balance. So it is in harmony and balance in nature or in a social relationship. Okay, so that's the symmetry is very important, and symmetry is also useful in explaining various spectroscopy, where you may study in the future as a Raman spectroscopy or infrared, how the symmetry of the molecules that play important role that gives rise to a spectrum. So even the Rangoli, if you look at it, I can view this scientifically. If you put an axis here, a 6-fold axis, then I rotate 60 degrees. So this will come here, or the total thing will move here, another 60 degrees, another 60 degrees, like this. So I have a C6 axis along the center of this point. So you can rotate. So that's a symmetry. Why this Rangoli looks beautiful is because it is symmetry. Suppose I don't have few things here, then it's incomplete. Okay, so that's where you have to view in a scientific manner for anything. So you can find a reason. There is something is interesting. So again, looking at the electromagnetic spectrum, see today now I'm able to speak to you because of the technology. We are using the microwaves to use the transmission, so we use the internet, everything. So now if you take electromagnetic spectrum, I'm going to show some of the things in the ultraviolet or visible light, okay, the light emitting material, how we are using them. So how the light is very important to our life. See, you can't imagine a day without sunlight. So if everything is dark, so our mood also goes down. Okay, so it's a gloomy. So we need light. So light is also a source of energy. So otherwise, the plants cannot produce the carbohydrates. So we will not have food. So light is the source of energy. So in ancient time, so people use the fire. So to make the light in the absence of sunlight, so in the evening or night, so you make the fire, and then came the candles and lamps, how to make these candles. So with the oil, you can also burn the lights. So then Thomas Alva Edison discovered the incandescent bulb. then we have fluorescent tubes, and now we are using the LEDs, light emitting diodes, which is made by semiconductors. So this is the growth of the LEDs. So it's more vertical. So it started in 1996, but its efficiency has been improved. So now we replace LEDs everywhere, and you can get a different colors by different ions. So here you might have seen the glow in the dark toy. So when you just shine for a few seconds, then you stop, switch off the light, so you can see they'll be glowing. So you can also paint them. So these are all made of strontium aluminum oxide with europium and dysprosium, which emits the europium emits the green color in these samples. So it's an application. Okay, so you can understand how they are. But LEDs, coming to LED, why we need LED is because so they are durable, so they are also compact, and you don't produce such heat as an incandescent bulb. Also, the energy, the amount of electricity consumed for lighting will be decreased by 50% if you replace all the incandescent bulbs. So that's why it's considered as important. So you have a LED chip on which you coat the phosphor grains, then you get a white light. So it's a simple physics, what you are studying in your higher secondary, maybe are taken from the 12th standard physics. So you can make a semiconductor like silicon. So you can replace one of the silicon with a group 5 element like phosphorus or arsenic, which has one extra electron, so that the material becomes rich in electrons, so electrons can move. It's called the N-type. On the other hand, you can also replace the silicon with a group 3 element like aluminum or boron, which has only 3 valence electrons. So there is a shortage of electron to form the bond. So to fill this, another electron moves from here, leaving a vacancy that's called holes. So then this is called a p-type. So now if you make a silicon both N-type and p-type and make a junction, so you are making a p-n junction. So you have N-type this side and the p-type here, you have this junction here, and then the charges will move towards the other side because of the opposite charge of the vacancy created. So, and this is the PN junction, what is used in your LEDs. So if you make a PN junction, then you connect it to a potential difference you create. So electrons will move from here to here and the holes will move. When they move, they recombine because they are opposite. So when they recombine, they give the energy in the form of light. So that's how these LEDs work. And to get a white light, again, we have a different strategies. Either you can mix the primary colors, the blue, green, and red, or you can take a LED which emits a blue or in the ultraviolet, then coat the phosphor, that's a powder, the light emitting powder which I have shown earlier. So these 3 different colors, then again you mix white, or what commercially we are using white LED is having a blue LED, which is based on indium gallium nitride. You can coat a phosphor powder on that. So this emits yellow, but it absorbs part of the blue to get excited. So you get some blue and yellow is again a combination of the red and green. So you get again the primary color, you get a white LED. So that's how here we have here that's made by Japanese company Nishia and other companies are using it. So you have this compound with the yttrium, aluminum oxide with cerium, which emits the yellow here, and this blue emission comes from your LED chip. So then you get a white emission. So that again, it has changed the technology. Okay, so if you look at the old television or the computer monitor, it has a cathode ray tube. So now later it was replaced with the plasma display. Then now we are using LED. So that is the LED light is used as a backlight. So that is shining on your pixels, and then you get the colors on this. So your screen has become very thin now. So that is also, you can see it is finding application in the traffic signals or signboards or the 3D LED TVs. And even the London Bridge, the lights have been replaced with the LED lights now, so that they could save a lot of electricity. So this was again considered as a Nobel Prize in 2014 in physics for the discovery of energy efficient and environment friendly light source as a blue light emitting diode. So you may question here, why only for blue, what not about the red and yellow LEDs, which was discovered much before. But it was a difficult task to make blue LED. It took several years for different people to work on this. So that's how, without blue LED, now we cannot use as a white light, or we cannot use for other applications. So it was considered very important. So it was Professor Isamu Akasaki and his student Hiroshi Amano and Shuji Nakamura from industry. So these three people, they started working from the 1970s, and then they made how to grow this gallium nitride. The challenge was growing a gallium nitride thin film. So yes, so this is taken from Hiroshi Amano's Nobel lecture. So here you can find the growth of aluminum nitride was made from Akasagi's lab, so 1967. But then Hiroshi Amano was thinking as a student how to reduce the size of this brown tube. So how, if you can achieve a blue LED, then you can change the world. So he joined in his group and graduated. So that's how they found the nitride-based blue LEDs. So it took several years and the difficulty involved to make these thin films of gallium nitride, but now they could make it. So then in the 90s, it has come as a commercial product. So now we can find how the laureates challenge the established truths. So like Raman, why the sea is blue, it was already known it is a reflection of the sky, but he then challenged, no, there may be some other reason. So similarly, these LEDs, so they made a lot of hard work and took several experiments and learned the technology, carried thousands of experiments, which you might have heard from Thomas Alva Edison's discovery of the incandescent bulb. He made 1,000 experiments and finally he could succeed. So same things happen. So, and most of the time they failed, but they never gave up. So this was laboratory artistry, what you gain by doing several experiments. Now you can imagine the LEDs application. See, these are some of the remote village where you cannot have the electricity grid. So you can also use, the children use these LED lights for the studying in the night. So how they do is they have a solar cell which converts the solar energy into electrical energy stored in the batteries. Then you can use in the LEDs. Again, when you talk about the batteries, there is another Nobel Prize was awarded in chemistry in the year 2019 to Professor John Goodenough and Professor Stan Whittingham and Akira Yoshino. So Professor Goodenough is the oldest person in chemistry to receive the Nobel Prize at the age of 96. So he still works on the lab. So you can see how they made it. It was a Stanley Whittingham. First he showed if you take a lithium metal combined with another titanium sulfide, which has a layer structure, so lithium can enter into the structure if you charge it or discharge, so you can do this. But it can produce only 2 volts, but it was good enough to replace this sulfide with the oxide so that you can increase the potential, so you can make a 4-volt batteries. But both case problem is you're using the lithium metal on the other side, it's not safe to handle several such batteries exploded in their experiments. So it was the Yoshino from Japan. So he used, instead of the lithium metal, he used a coke, petroleum coke, the carbon, so which has a graphite, so layers. So the lithium can go inside the layer. So that's what now we are using in all our batteries. So that is, see, that's what they made the experiments in the year 70s. So if you remember Alfred Nobel's will, the one which discovery should be useful to the humankind. You imagine how many years it has taken. And that's why nobody is working to get a Nobel Prize. So their work is taken in the long run. They find their work is important in the society. So they are selected for the Nobel Prize. Okay. So you keep doing your work. Okay. So the recognition comes later. So materials, if you take, again, it's an interdisciplinary area like chemistry we need to synthesize material to understand how to change the materials, and physics is important to understand the properties, and engineering comes when you want to make a materials or the product. Okay, so it's an interdisciplinary area. And when you talk about again material, maybe I'll take another 5 minutes or so. So we have different sizes. You may have heard the name nanomaterials. That's in the size of 10⁻⁹ meters. So the word nano was coined by Norio Taniguchi in the year 1974. Now you can imagine why Michael Faraday never called this gold as a nano, because the word was not known earlier. Okay, so nanotechnology is the engineering of functional system at the molecular scale. The first book on nanotechnology was written by Eric Drexler on the topic is engines of creation, the coming era of nanotechnology. So if you want to compare the size, human hair is 50,000 nanometer thick, whereas the diameter of a water molecule, H2O, is 0.3 nanometer. The carbon nanotube, the width is only 1 to 2 nanometers. But now we can also make transistor 20 nanometer, and DNA width you can see 2.5 nanometer, or the protein width is 10 nanometer. Now, if you want to get a bigger idea, you can compare. This is the diameter of our Earth, so which is 12,756 kilometer. That is 1.27 10 power plus 7 meters. You compare again with the football, so it is only 22 centimeter diameter, so it's 0.22 meter. But the same carbon C60 molecule, its diameter is 0.7 nanometer, that is 0.7 into 10 power minus 9. So now you imagine what is the dimension you are talking about. So this cannot be seen. So we need techniques to view this size of this material. Again, in the nano, another important name is Richard Feynman. He's an American theoretical physicist, also a Nobel laureate in 1965. So he made his famous statement, whenever you come across nano, you hear this, there is a plenty of room at the bottom. The meaning is when you dig or when you go down or downsize your material, you have more opportunity, more challenges, more interesting properties. So he also posed a question, what would happen if you could arrange the atoms one by one the way we want them? Is it possible? So this was the question, just remember this question. So also we know in Ayurveda, the gold plasma is a fine particle of gold. So we micron to nanometer size. See, the bulk gold cannot have any property. You cannot take bulk gold, but when you grind it into a small size, then it has more medicinal applications. So its constituent, it has a gold, silica, all this constituent. So it has been analyzed, published. So that's why when you reduce the size, so you get interesting properties of material. So even the butterfly, we see they are colorful, their feathers or wings, so more colorful. How that's happening? So if you take the small portion of the butterfly wing to electron microscope, so you can see the nice views. And again, you enlarge, you can focus on this small region. So if you enlarge, you can see the pattern, so which is well arranged in a close proximity. So it's called optical grating. So when you have optical grating, when light falls, you get a reflected with the different colors. So you can separate them or get a different colors. So that's how the butterfly wing, which is naturally arranged. So that's why to try to understand, now it is possible to make such structures in the laboratory to have a much better optical gratings at the nanoscale. So it's a development in nano materials has become because our observation, so the instrumentations have been developed. For example, our eye, so which has a sensitivity, you can see only 1/10 of a millimeter. If there's some particle is 0.1 millimeter, you can see through our eye. If it's smaller than that, we cannot see, but we can use optical microscope. That can also, again, it's a 1 micron, that is 10 power minus 6 meter. But what the nanomaterials is 10 power minus 9 meter. So that means we need the electron microscope because electron has a dual nature. So we can use here the wave nature to tune this with the different force or the voltage. So we can finely tune this to get the atomic resolution. So also it is a famous again in the nano, how it has made. So Gordon Moore, so who is a co-founder of the Intel. So he made a famous statement, it's already called Moore's law, that the number of transistors on a chip roughly doubles every 2 years. So he made in the years late 60s. So it is the graph what he has made. So you can see now the number of transistors. So as the year progressed, now we have about 10 power 10 or even much more. So that's how the size of our devices have narrowed or reduced. So here you can see we can use the carbon nanotube as your transistor. So we have a source and drain. So the distance between them is only 18 nanometers. So that's the advantage of this size reduction. So which we have seen here, the first generation computers, how big it is. It's taking a big hall size, but then the second, third, fourth, fifth, now we are in the world of tab, okay? So the size reduction is possible because of the size in the transistors and the electronics. Okay, now if you remember the question by the Richard Feynman, so is it possible to arrange the atoms one by one? We want, yes, the dream comes true. Here I'll show a picture where IBM, they've written on a nickel plate. So you use the xenon atoms, so we can have few atoms like this, so you can arrange like a IBM. So it is used using a scanning tunneling microscope. So you can control how the atoms you can deposit here. So it is possible. Okay, if you also look at some of the numbers, so what we have is given in the world Tamil literature. So we have Anu, that is called atom. So we can see this in numbers, so 1 divided by 10 power 9, that's almost nanometers. And this one is angstrom, that's atoms are in that range. But still, can you imagine this number? What will be the fraction what we get? So is it possible for us to reach that level? So it may be possible. So sometimes, so we have to find out how to do this. So like going to the femtometers or even much below. So that means it's, so again, you have to look in a scientific way how to find out this. So it is now possible here. So why not? We can go further. So also there are a lot of opportunities women in science. I just want to cover here. We know the famous Marie Curie. So she was actually rejected by university because she's a woman, but she's the only one who won 2 Nobel Prize, one in women in physics and chemistry. So make this statement: be less curious about people. Don't worry about people. Who is who? What is they do? Everything. So just be curious about your ideas. So that will make you more interesting on your environment. Why this is happening like this? What is the science behind this? So okay, so then it is more interesting to know. So of course we have a lot of Indian women in science, like Dr. Janaki Ammal, so who was a founder fellow of the Indian Academy of Sciences, and Anandibai Joshi was the first woman who went to abroad to USA to get a medical degree. So this is the first woman in 1885, and she was born in 1865. Imagine those days going abroad as a woman to get a degree. We have also a Chatterjee, so who was also worked on different fields. And we have Kamal Ranade. She was also received the worked at the Cancer Research Center. So she worked with the bio-related thing, also in the field of leprosy. So, and Radha Balakrishnan, who is again a Fulbright awardee and a senior associate with the Theoretical Physics Center at Italy. So you can find a lot of information on the Indian Academy of Sciences website, so you can get more information. And not only that, you can also get a scholarship. So we have for the school children to further pursue. So there is a KVPY program. So Kishore Vaigyanik program. So where you can get the fellowship for 5 years. So you can, if you are good at your schools, and there is an entrance exam. So I follow this one. So that is a famous statement by Alexander Fleming, that never neglect an extraordinary appearance of or happening, which may be in your results. So usually people neglect a lot of results, which may be small signal, but it may be an important clue. So that's what he says, one sometimes find what one is not looking for. That happens in science many times. You want to prepare some material or synthesize some of the organic molecule, you never end up with the same, but you get at something else. So then try to look at what is the other one. So then you can get better properties. So same thing by Woodward. So you can look at it, and yeah, I can quote some of few things by Sarvapalli Radhakrishnan. So we celebrate the Teachers' Day. So Mother India expects of you that your life should be clear, noble, dedicated, selfless work. So when you want to climb the mountain, you should have a strong base. That means you should have good strengthen your legs. So that means your basics should be stronger. So whatever you study now, you are going to extend further and further. So that's why I showed some of the examples from your textbook. So that's going to be there for you when you continue. Okay. So, okay, maybe I'm almost done. So you can say these 2 Tirukural. So water will flow from a well in the sand in proportion to the depth to which it is dug. So you dig more and more, you get more water, and every time you remove the water and more more water will be there. So that's how knowledge will flow from a man in proportion to his learning. So learn whatever possible, learn more. So then you can get more knowledge. And also to discern the truth in everything by whomsoever spoken is wisdom. So if you want to know whatever I have shown, I just showed some glimpse. So you can explore more. You can, nowadays information is available in your fingertip. Just type in Google. So you only need your fingertips to type. So you get all information. So you can find out whatever I said is true or how it is. You can also explore more. So you can, what you can contribute, or you can argue, and you can prove or disprove. So it's possible. That's how the wisdom grows. And my last slide from Swami Vivekananda, that stand up, be bold, be strong, take your own responsibility, okay? So on your own shoulders. All the strength is within yourselves, so you can make your own future and keep going. So that's what my message. I don't have any summary, so I just summarize. So what is science, how it motivated people, and how it motivates even us. So why should we pursue science? So to understand the nature or the surrounding. So that's how we make a lot of discoveries, and it's useful to our mankind. So we imagine. So I wish all of you all the very best, and you can welcome to the science, and you can do whatever science you are doing. Even engineering has the basic science there. Okay, so I wish you all the good luck, and sorry I've taken a little more time, and I'll be happy to answer any of your queries. Thank you.
Thank you very much, Dr. Lakshminarasimhan, and especially because such an early morning for you, and
Oh,
although it's a Saturday late evening, but the way you have this whole journey, right from, I'll say, from physics to chemistry to electronics, touching upon each and every aspect, coming down to 18 nanometer of transistors, which I just shared that we'll be celebrating this year
yeah.
also. So that's very nice of you. There are a few questions which are there in the chat section.
Yeah,
I'll
please.
just take one by one. So the first one is it true to say that energy exists in either waveform and particle form, and only there is no other form of energy? I think that must be in the very initial part of your talk, which you touched upon.
Yeah, I showed about the light energy, am I right? So it was believed that the light has the wave nature, but it was also shown the particle nature. Okay, light has a dual nature. So yes, energy is stored in the form of photons, h nu, and yeah, wave also has energy. Okay, so it's a dual form. How you use that, whether as a particle or as a wave. So it is, yes, it is existing. So we might have heard about particle accelerators, so which produce large energy, huge energy. And wave also produces energy. Like we have the sea, the waves. So that's one of the way of getting energy, the tidal energy. So, but in this case, of course, light, yes, it has both forms as energy. See, whatever light you are shining, it comes out. So as you are seeing as a wavelength, the light, so colors, so emitting color are the colored objects, so which absorb some portion of the light and emits the other color, other wavelengths. So you see the object as a color. Yes, it is possible, both form.
Okay, I'll take up the next one. Um, what would be the ideal source to use for measuring Raman spectra?
Well, there is, as I mentioned, the Raman spectrum. So it was used with earlier days with the light source, but now with the laser. So laser Raman is more famous. So to find out, so that's how actually the Raman spectrum was even has become more application oriented based on the discoveries made in the laser in the 60s. So if I'm right, around 1965, I'm not very sure. But once the lasers have come out, so then it is a source of Raman spectrum. So now we all use a different way, lasers like 532 nanometers or 350 nanometers. So sometimes some of the samples will also give light fluorescence. So then you cannot use a particular laser. So you need to choose what is the wavelength of your source laser. So nowadays it's possible, even the same instrument, you can change the laser source of the laser wavelength. So you can get your Raman spectrum. So that's the source here. Okay, it's a light source. Okay, so but in the form of here we are using laser as a particular wavelength.
Okay. The next is, organo catalysts are useful for human beings? Can you
Of
explain?
course, yes. So the discovery has gone this year for asymmetric organocatalysis because they are useful in the pharma industries. That's how they revolutionized after their first publication in the year 2000. So many of the pharma companies, for example, I think there are some molecule uh, which is long chain molecules. So it has been made. It was having, of course, it is poison, but it was having some 100 steps, about 100 steps. But now that is possible only to make within 23 steps of synthesis, and it has increased by 7,000 times more your product. Earlier, it was you get only 0.0009 grams or something, but now you can get in large scale, about 7,000 times it was improved. I think it is stacnine, it is available in the information from the Nobel website. So that's how these organocatalysts reduce several steps of large synthesis steps. So that is the importance, and most of the pharma companies started using this. So then, see, otherwise they won't consider this as for the Nobel Prize. So it is useful in that's how when it is used in the pharma industry, it's useful for us. So for to treat the our disease, okay, so you can design some of the molecules so easily by using this organocatalyst.
Okay. The next one is, how can we recombine the components of white light after a prism has separated them?
Well, it's a separation by prism. So I know it's you can split the white light into a different wavelengths. But in this case, what we are doing is you selectively use some of the wavelengths. For example, if you have a phosphor material, as I shown here, so if it has a europium as its emitter, it will only emit in the red. So selectively it will emit. So you use a material for different colors, like terbium, it will give a green. So that's how you get, without combining here, so we get use a different material which emits a particular wavelength. So once white light is split into separate wavelengths, but then it's going to be a different colors. But here what you use is a different colors to combine to get a white light. So it's a reverse what we are doing, combining the primary color, blue, green, and red, so to get the white light. So if you mix blue and green and red in equal proportion, 1/3, 1/3, 1/3, so you get a white. You can mix the paint so you can see that.
Okay. I'll take up the last two questions now. The first one is, what is the use of Raman spectroscopy in medicine? And the second is, how does quantum theory explain the photoelectric effect?
Well, so the Raman spectrum is useful in the medicine. That means to understand the cell structure, it's an imaging technique now. Okay, so as I shown here, so you can image your materials like tissue cells. So that is one of the application what we can see. So any changes happens in your tissue cell or the binding of the sites, any change happens, then you see difference in the molecular vibrations. So for example, lipids show here or phosphates show here the stretching. So if there is some damage to some of the proteins or the lipids or their binding sites, so you can see there is a shift. So that's how you can use this in the form of in the medicine. So you can use this. And coming to other question, the quantum theory, of course, it was explained that is useful in explaining the photoelectric effect because it's considered as a photons, and then the quantum particles having a quantized energy. So each particle has a definite energy, quantized energy levels. So that's where the quantum theory comes into picture compared to the classical theory. So that is useful in explaining the photoelectric effect. So photons which have quantized energy, so definite energy, it can be discrete energy levels. So you have the quantized levels of energy. So that has particular energy. So that's coming from the quantum theory, which has been developed later further.
Okay. So I think I've taken up all possible questions. Thank you very much, Dr. Lakshminarasimhan, for sparing your valuable time with all of us, and especially enlightening all the students. Some of them, I suppose, they must be from the undergrad and postgrad level also, or some maybe from faculty members also.
Oh,
And
okay.
I can see the wide variety of questions which have been asked. So definitely, the level is definitely
Yeah,
not. It's beyond
I
us. Yeah,
yeah,
it's yeah,
yeah. I
yeah,
also take this opportunity. Thank you very much for arranging such wonderful event and to interact with. At least we are a small level of motivation. Okay, so we are
exactly,
not very there. At least this gives us some motivation to pursue what we do research. But of course, we are not talking too technical, but just to have a motivation. And I also learn because with you, I also come to know a lot of information and learn still. See, life is never, learning is never in process. So it's a lifelong, that's a scholar. Okay. So I also do the same thing along with you. Okay. And thank you for making this wonderful event and the opportunity to interact with the students and yourself.
sure. Thank you very much.
Thank you very
Okay,
much. Thank you.
okay.